Imagine a place where time itself slows to a crawl, where gravity becomes so intense that not even light can escape its grasp. These aren't the creations of science fiction writers or fantasy novels. They're real objects scattered throughout our universe, hidden in the darkness between the stars. Black holes. Let's begin our journey at the very edge of possibility, where the familiar laws of physics begin to bend and break. The term black hole wasn't coined until 1967, when physicist John Wheeler used it during a lecture. Before that, these cosmic enigmas were called frozen stars or collapsed stars, names that somehow feel less ominous, less final. But what exactly is a black hole? At its most fundamental level, a black hole is a region of space-time where gravity has become so powerful that it warps the very fabric of reality. To understand how this happens, we need to think about what holds a star together in the first place. Stars spend most of their lives in a delicate balance, gravity pulling inward, trying to collapse them, while the nuclear fusion in their cores pushes outward with tremendous pressure. This cosmic tug-of-war can last for billions of years. Our own sun has been locked in this balance for about 4.6 billion years, and will continue for billions more. But all things must end. When a massive star, at least 8 times the mass of our sun, exhausts its nuclear fuel, that outward pressure suddenly vanishes, and gravity wins. The collapse of a massive star into a black hole happens incredibly quickly, in less than a second. One moment, you have a star larger than our entire solar system. The next moment, all of that mass compresses down into an infinitely small point called a singularity. Picture it, matter compressed so densely that all the mass that once made up a giant star now occupies essentially no space at all. The mathematics describing this point become infinite, breaking down entirely. This is where our current understanding of physics reaches its limit. Surrounding this singularity is the event horizon, the point of no return. The event horizon isn't a physical surface. You couldn't touch it or stand on it. It's simply the boundary where the escape velocity equals the speed of light. Once anything crosses this invisible line, whether it's a particle of light or a spaceship, it can never return to the outside universe. The radius of this boundary depends entirely on the black hole's mass, and there's even an equation for it. The Schwarzschild radius defines the size of a black hole's event horizon. For a non-rotating black hole, this radius equals approximately 3 kilometers for every solar mass. So a black hole with the mass of our sun would have an event horizon only 6 kilometers across, smaller than most cities. A black hole with 10 times the sun's mass would have an event horizon about 30 kilometers in diameter. But black holes come in different sizes, and this brings us to a fascinating hierarchy. Black holes are categorized into 3 main types based on their mass. Stellar mass black holes form from collapsed stars and typically range from about 5 to several dozen times the sun's mass. Intermediate mass black holes range from hundreds to thousands of solar masses, though these remain somewhat mysterious and rare. And then there are the giants, supermassive black holes, which lurk at the centers of galaxies and can be millions or even billions of times more massive than our sun. Our own Milky Way galaxy harbors one of these monsters at its heart. At the center of our galaxy, approximately 26,000 light-years from Earth, sits Sagittarius A star, a supermassive black hole with a mass of about 4.1 million suns. Despite its incredible mass, we've only recently been able to image it directly. For most of history, we knew it was there only by watching stars near the galactic center whip around an invisible point at incredible speeds. These orbital observations revealed something extraordinary about how we detect black holes. Black holes themselves emit no light. That's why they're black. But we can observe them through their effects on nearby matter. As gas and dust spiral inward toward a black hole, friction heats this material to millions of degrees, causing it to emit intense X-rays and other radiation. This glowing disk of doomed matter, called an accretion disk, can outshine entire galaxies. So ironically, some of the brightest objects in the universe mark the locations of the darkest. And there's one more crucial fact to understand as we begin this journey. According to Einstein's theory of general relativity, time itself behaves differently near a black hole. The closer you get to the event horizon, the slower time passes relative to someone far away. If you could somehow survive hovering just outside a black hole's event horizon for what felt like 1 hour to you, when you returned to Earth, decades or even centuries might have passed. This isn't science fiction. It's a fundamental prediction of physics, confirmed by countless experiments. So now we know the basics. Black holes are regions of spacetime with gravity so intense that nothing can escape them. They form when massive stars collapse, creating an infinitely dense singularity surrounded by an event horizon. They come in different sizes. They bend time itself, and while invisible, they reveal themselves through the light of matter spiraling to its doom around them. But this is only the beginning. There is so much more to discover about these cosmic mysteries, from the theories that predicted them to the strange phenomena that occur in their vicinity, to the very real possibility that tiny black holes might be evaporating right now through a process discovered by Stephen Hawking. Let's continue deeper into the darkness where the truly strange awaits. Before black holes were discovered in space, they existed in the human mind. They were mathematical ghosts, theoretical constructs that emerged from equations almost by accident. And the story of how we came to understand them is as fascinating as the objects themselves. The first hint of black holes came in 1783, when an English clergyman and natural philosopher named John Michell proposed the existence of dark stars. Using Newtonian physics, Michell calculated that if a star were massive and compact enough, its escape velocity would exceed the speed of light. Even then, more than 2 centuries ago, thinkers understood that light had a finite speed, and Michell realized this meant such objects would be invisible, their light forever trapped by their own gravity. But Michel's dark stars were just the beginning. The real breakthrough came much later, buried in the equations of a new theory. In 1915, Albert Einstein published his general theory of relativity, which reimagined gravity not as a force, but as a curvature of space-time itself. Mass bends the fabric of space and time around it, like a bowling ball placed on a stretched sheet. Within months of Einstein publishing his theory, a German physicist named Karl Schwarzschild found an exact solution to Einstein's field equations. While serving on the Russian front during World War I, Schwarzschild's solution described something impossible, something so strange that even Einstein rejected it at first. Schwarzschild's mathematics predicted that if enough mass were compressed into a small enough volume, it would create a region from which nothing could escape, what we now call a black hole. But here's the remarkable part. Schwarzschild made this calculation while in the trenches of World War I. He sent his solution to Einstein from the battlefield. Tragically, Schwarzschild died just a few months later from an illness contracted during the war, never knowing that his equations would one day be confirmed by astronomical observations. For decades, physicists debated whether these mathematical curiosities could actually exist in nature, or if they were merely artifacts of the equations, mathematical phantoms with no physical reality. The universe, however, had already been creating them for billions of years. The first stellar mass black hole candidate was discovered in 1964, though it wasn't confirmed as a black hole for several more years. It was found in the constellation Cygnus and designated Cygnus X1. Astronomers noticed an intense source of X-rays paired with a visible blue supergiant star. The visible star appeared to be orbiting an invisible companion, something massive enough to be a black hole, but completely dark. The evidence was compelling. Matter from the blue supergiant was being pulled away and heated to millions of degrees as it spiraled into the unseen companion, producing those powerful X-rays. This discovery opened our eyes to a new population of objects hiding in the cosmos. But it also raised new questions about the bizarre physics at play near these extreme objects. Black holes don't just bend space, they can also spin, and when they do, they drag space-time itself around with them in a phenomenon called frame dragging, or the lens-thirring effect. Imagine a black hole as a drain in a bathtub, but instead of water swirling down, it's the very fabric of space and time that's being twisted. Anything near a rotating black hole, even light itself, gets pulled along in the direction of the spin. This creates a region called the ergosphere, just outside the event horizon, where it's impossible to remain stationary. You would be forced to move in the direction of the black hole's rotation, whether you wanted to or not. The mathematics of rotating black holes revealed something even more bizarre. A rotating black hole is described by the Kerr metric, named after New Zealand mathematician Roy Kerr, who solved the equations in 1963. Unlike a non-rotating Schwarzschild black hole with its spherical event horizon, a rotating Kerr black hole is flattened at the poles and bulges at the equator. It's oblate, like a cosmic lentil. The faster it spins, the more distorted it becomes. And here's where it gets truly strange. The mathematics suggest that inside a rotating black hole, the singularity isn't a point, but a ring. This ring singularity leads to one of the most speculative and fascinating ideas in all of physics. Some solutions to the equations suggest that a rotating black hole might contain a passageway, a path that avoids the singularity entirely and could theoretically lead to another region of space-time, or even another universe. These hypothetical tunnels are called Einstein-Rosen bridges, or more popularly, wormholes. Before you pack your bags for interdimensional travel though, there's a catch. These wormholes will be wildly unstable, collapsing almost instantly. Most physicists believe that even if they could form, nothing could pass through them without being destroyed. They remain a beautiful mathematical possibility, but almost certainly not a practical means of transportation. Yet for all their strangeness, black holes follow rules, ironclad laws that govern their behavior. Black holes obey a set of principles known as the laws of black hole mechanics, which are remarkably similar to the laws of thermodynamics. The most famous is the second law. The total surface area of a black hole's event horizon can never decrease over time. Black holes can merge and grow, but they cannot spontaneously shrink. This connects to a deep concept. The surface area of the event horizon is proportional to the black hole's entropy, a measure of disorder or information content. In a sense, a black hole's event horizon is a record of everything it has consumed, encoded on its surface. This connection between black holes and thermodynamics led to one of the most revolutionary discoveries in theoretical physics. In 1974, Stephen Hawking made a shocking prediction. Black holes aren't entirely black. Using principles from quantum mechanics, Hawking showed that black holes should emit a faint thermal radiation due to quantum effects near the event horizon. This Hawking radiation means that black holes slowly lose mass over time. They evaporate. For a stellar mass black hole, this process takes an incomprehensibly long time, far longer than the current age of the universe. But for a tiny black hole, if such things exist, the evaporation will be much faster. A black hole with the mass of a mountain might evaporate in just a few billion years, ending its life in a final burst of radiation. So we've travelled from the trenches of World War I, where Schwarzschild first glimpsed these objects in mathematics, to the quantum realm, where Hawking showed they might eventually vanish. We've learned that black holes can spin, dragging space itself around them. We've seen how they follow laws similar to those governing heat and energy. And we've encountered the tantalizing, if impractical, possibility of wormholes. But there's still so much more to explore. What happens to the matter that falls into a black hole? How do supermassive black holes grow to such incredible sizes? And what strange phenomena occur in the most extreme environments around them? The journey continues into even stranger territory. One of the most profound questions about black holes is also one of the simplest. What happens to the things that fall in? Does the matter simply vanish from our universe? Is the information about that matter, its quantum state, its history, lost forever? This question has sparked one of the greatest debates in modern physics. When an object falls toward a black hole, something peculiar happens from the perspective of a distant observer. Due to extreme time dilation, the falling object appears to slow down as it approaches the event horizon, and its light becomes increasingly redshifted, stretched toward longer, redder wavelengths. From your safe vantage point far away, you would never actually see the object cross the event horizon. It would appear to freeze at the boundary, becoming dimmer and redder, fading away over time, but never quite disappearing. This is why black holes were once called frozen stars. They appear frozen in time from the outside. But the experience of the falling object tells a very different story. From the perspective of someone or something falling into a black hole, the journey to the event horizon takes a finite amount of time, and for a supermassive black hole, you might not feel anything unusual as you cross it. The event horizon isn't a wall or a barrier, it's simply a point of no return. For a large enough black hole, the gravitational forces at the event horizon are relatively gentle. You could cross it without even realizing it, at least initially. However, as you continue falling inward toward the singularity, tidal forces would grow increasingly extreme. These forces would eventually stretch you vertically while compressing you horizontally in a process astrophysicists call spaghettification. The term sounds almost comical, but the reality would be anything but. Spaghettification occurs because gravity increases with proximity to mass. If you were falling feet first into a black hole, the gravitational pull on your feet would be significantly stronger than the pull on your head. This difference in gravitational force, the tidal force, would stretch you like taffy. For a stellar mass black hole, this would begin well before you reach the event horizon, tearing you apart at the molecular level. But for a supermassive black hole, the event horizon is so far from the singularity that you could cross it intact and survive for a while longer before the tidal forces became lethal. Either way, the ending is inevitable: complete destruction at the singularity. This brutal fate for infalling matter connects to a profound mystery about information and reality itself. The information paradox is one of the deepest puzzles in theoretical physics. Quantum mechanics tells us that information cannot be destroyed. If you know the current state of a system perfectly, you should be able to reconstruct its past and predict its future. But when something falls into a black hole, it seems to disappear from our universe forever. And if black holes eventually evaporate through Hawking radiation, which appears to be random thermal radiation carrying no information, then where does that information go? Stephen Hawking initially argued that information was indeed lost, which would violate quantum mechanics. This sparked decades of debate, and most physicists now believe information must somehow be preserved, perhaps encoded in subtle correlations within the Hawking radiation itself, though exactly how remains unclear. While physicists wrestle with these quantum mysteries, astronomers have been making stunning discoveries about the largest black holes in existence. Supermassive black holes exist at the centers of most, if not all, large galaxies. The largest black hole discovered so far has a mass of approximately 40 billion times that of our Sun. That's roughly 40 billion solar masses concentrated in a region smaller than our solar system. To put this in perspective, if our Sun were a grain of sand, this black hole would be larger than a small house. These cosmic giants didn't form from collapsing stars. They're far too massive for that. Instead, they likely grew over billions of years by consuming gas, dust and stars, and by merging with other black holes as galaxies collided and combined. The relationship between these supermassive black holes and their host galaxies is surprisingly intimate. Astronomers have discovered a tight correlation between the mass of a galaxy's central supermassive black hole and the properties of the galaxy itself, particularly the velocity dispersion of stars in the galaxy's bulge. This relationship suggests that supermassive black holes and their host galaxies grow together, evolving in tandem over cosmic time. A black hole containing just 1,000% of its galaxy's total mass can somehow influence the structure of the entire galaxy. This happens through powerful outflows and jets of energy that the black hole produces as it feeds, which can heat or expel gas, regulating star formation throughout the galaxy. In essence, black holes help shape the very galaxies that harbour them. Some of these supermassive black holes are actively feeding, creating some of the most spectacular phenomena in the universe. When a supermassive black hole actively consumes large amounts of matter, the system is called a quasar, or active galactic nucleus. The accretion disk around an actively feeding supermassive black hole can shine with the luminosity of trillions of stars, outshining the entire galaxy that hosts it. These brilliant beacons can be seen across vast cosmic distances. In fact, the most distant quasars we've observed are so far away that we're seeing them as they were when the universe was less than 1 billion years old, less than 10% of its current age. They give us a window into the early universe, showing us that supermassive black holes form surprisingly quickly after the Big Bang. And some of these black holes don't just shine, they shoot. Many supermassive black holes launch enormous jets of plasma and radiation from near their event horizons, perpendicular to their accretion disks. These jets can extend for hundreds of thousands or even millions of light years, far beyond their host galaxies. The jets are powered by a combination of the black hole's rotation and powerful magnetic fields in the accretion disk. Material in these jets travels at a significant fraction of the speed of light, and they pump enormous amounts of energy into intergalactic space. These relativistic jets are among the most powerful and energetic phenomena in the universe, visible across the entire electromagnetic spectrum, from radio waves to gamma rays. But not all black holes are actively feeding. Most, in fact, are quiet. The supermassive black hole at the center of our Milky Way, Sagittarius A star, is relatively quiet and inactive. It's not consuming much matter at the moment, so it doesn't have a bright accretion disk or powerful jets. Astronomers estimate it consumes only about the mass of a single asteroid per year. This is fortunate for us. If it were an active quasar, the radiation from our galactic center would make life on Earth far more challenging, if not impossible. But Sagittarius A star hasn't always been quiet. Evidence suggests it was much more active in the past, and it likely will be again in the distant future, particularly when the Milky Way collides with the Andromeda galaxy in about 4 billion years. We've journeyed now from the fate of individual particles falling through event horizons to the cosmic giants that shape entire galaxies. We've encountered paradoxes that challenge our understanding of information and reality. We've seen how black holes grow from millions to billions of solar masses, how they form partnerships with their host galaxies, and how some transform into brilliant quasars, while others slumber quietly in the dark. But there are still mysteries to uncover. Stranger forms of black holes, the sounds they make when they collide, and the revolutionary ways we've learned to detect them. Let us venture further into the cosmic darkness. For most of human history, black holes existed only as theoretical possibilities, invisible and untouchable. We could infer their presence by watching stars orbit around them, or by detecting X-rays from their accretion disks. But in the 21st century, we've developed entirely new ways to observe these cosmic phantoms, not by seeing them, but by listening to them. On September 14th, 2015, humanity heard black holes for the first time. Two detectors in the United States, part of the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected a signal that lasted only a fraction of a second, a chirp in the fabric of space-time itself. This signal was produced by two black holes, each about 30 times the mass of our Sun, spiraling together and merging into a single black hole 1.3 billion light years away. The collision released more energy in gravitational waves than all the stars in the observable universe were emitting in light at that same moment. This detection confirmed Einstein's century-old prediction that accelerating masses create ripples in space-time, and it opened an entirely new way of observing the universe. Gravitational waves give us access to events that produce no light at all. When two black holes merge, they don't emit light. There's no material present to heat up and glow. No accretion disk. Nothing to see with traditional telescopes. But as they orbit each other in their final moments, they distort space-time so violently that they send gravitational waves spreading outward at the speed of light. These waves are incredibly tiny by the time they reach Earth. LIGO's detectors measure distortions in space-time smaller than 1,000th the diameter of a proton. To achieve this, LIGO uses laser beams traveling through 4-kilometer-long vacuum tubes, measuring the infinitesimal stretching and squeezing of space itself as gravitational waves pass through. It's one of the most precise measurements ever made in science. And these detections have taught us something surprising about stellar mass black holes. Before LIGO, astronomers had identified only about 20 stellar mass black holes in our galaxy, all found through X-ray observations of binary systems. LIGO has now detected dozens of black hole mergers, revealing a population of black holes we never knew existed. Many of these black holes are heavier than theories predicted, some exceeding 50 or even 100 solar masses. This suggests that our understanding of how massive stars evolve and collapse needs revision. These heavy black holes might form in environments with less heavy elements, or they might grow by merging with other black holes or neutron stars. Each new detection refines our understanding of these objects and their origins. While LIGO listens to stellar mass black holes colliding, other projects are working to detect even more massive mergers. Pulsar timing arrays are attempting to detect gravitational waves from supermassive black hole mergers. Collisions involving black holes millions or billions of times more massive than our Sun. These mergers produce gravitational waves with much longer wavelengths, creating ripples in space-time that oscillate over years or decades rather than fractions of a second. To detect them, astronomers precisely monitor the timing of signals from pulsars, rapidly rotating neutron stars that act like cosmic lighthouses. Gravitational waves passing through our region of space would cause tiny variations in when we receive pulsar signals. In 2023, several pulsar timing array collaborations announced evidence of a gravitational wave background, a cosmic hum of countless supermassive black hole mergers occurring throughout the universe. But gravitational waves aren't the only breakthrough in black hole observation. We've also learned to see them directly, or at least their shadows. In April 2019, the Event Horizon Telescope collaboration released the first ever image of a black hole shadow. This wasn't a photograph in the traditional sense. It was synthesized from radio telescope observations made simultaneously by 8 telescopes scattered across the globe, from Hawaii to Antarctica, effectively creating an Earth-sized telescope. The target was the supermassive black hole at the center of the galaxy M87, about 55 million light-years away, and containing 6.5 billion solar masses. The image showed a bright ring of radio emission from hot plasma surrounding a dark central region, the black hole's shadow. This shadow is larger than the event horizon itself, because the black hole's gravity bends light from behind it around its edges, creating a silhouette about 2.5 times the diameter of the event horizon. 3 years later, they captured another iconic image. In May 2022, the Event Horizon Telescope revealed an image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. Despite being much closer to us than M87's black hole, Sagittarius A star was actually harder to image. Although it contains only about 4 million solar masses compared to M87's 6.5 billion, the surrounding material orbits much faster, completing a circuit in minutes rather than weeks. This meant the material was changing constantly during the observation period, making the image much more challenging to reconstruct. The result, however, was stunning. Our own galactic center's black hole, its shadow captured for the first time, looking remarkably similar to its much larger cousin in M87. These observations have confirmed predictions and revealed new mysteries. But they've also highlighted just how extreme the environment around a black hole truly is. Near the event horizon of a spinning black hole, space-time itself is dragged along so powerfully that there exists an innermost stable circular orbit, the closest distance at which matter can orbit without inevitably spiraling inward. For a non-rotating black hole, this orbit sits at 3 times the Schwarzschild radius. But for a maximally spinning black hole, it can be much closer, just 0.5 times the Schwarzschild radius. Inside this radius, there are no stable orbits at all. Everything is doomed to fall inward. This innermost stable orbit marks the inner edge of the accretion disk, where material makes its final plunge. As matter crosses this boundary, it releases a final burst of energy before disappearing forever beyond the event horizon. The extreme conditions near black holes create natural particle accelerators more powerful than anything we can build. In the intense magnetic fields near black holes, particles can be accelerated to incredible energies, approaching 99.99% of the speed of light. These accelerated particles produce high energy radiation across the spectrum, from X-rays to gamma rays. Some of the most energetic cosmic rays detected at Earth, subatomic particles traveling at nearly the speed of light, may originate from the environments around supermassive black holes. The jets launched by these black holes can also accelerate particles to extreme energies, creating natural laboratories for studying physics at energy scales we cannot reproduce on Earth. We've traveled now from the subtle whispers of gravitational waves to the roar of colliding black holes. We've witnessed the first images of black hole shadows, both distant and local, captured by a planet-sized telescope. We've explored the innermost stable orbits where matter makes its final journey, and the extreme particle acceleration that turns black hole environments into cosmic accelerators. The picture is becoming clearer, but questions remain. Are there other types of black holes we haven't yet discovered? Could black holes be connected to the very structure of the universe itself? And what role might they play in the distant future of the cosmos? The story deepens, and the universe has more secrets to reveal. Black holes come in many sizes, from stellar remnants to galactic giants. But could there be black holes even smaller than those formed by collapsing stars? And at the other end of the scale, could there be something even more exotic hiding in the cosmos? Primordial black holes are hypothetical black holes that could have formed in the first fraction of a second after the Big Bang. Unlike stellar black holes that form from collapsing stars, primordial black holes would have formed from extreme density fluctuations in the very early universe, where regions of space were compressed so intensely that they collapsed directly into black holes. These could range from microscopic, smaller than an atom, to thousands of solar masses. If they exist, small primordial black holes would have already evaporated through Hawking radiation, but larger ones could still be around today. Some scientists have even proposed that primordial black holes might account for some or all of the mysterious dark matter that makes up most of the universe's mass. The search for these ancient objects continues, but they're not the only exotic possibility. Intermediate mass black holes, ranging from about 100 to 100,000 solar masses, are something of a missing link in black hole evolution. They're too massive to form from a single stellar collapse, but too small to be the supermassive black holes at galactic centers. Scientists have found only a handful of convincing candidates for intermediate mass black holes, often in dense star clusters or in small dwarf galaxies. One leading theory suggests they might form when stars in extremely dense clusters collide and merge repeatedly, creating ever more massive stars that eventually collapse. Another possibility is that they're the seeds of supermassive black holes, starting small in the early universe and growing over billions of years into the giants we see today. But beyond these puzzles about black hole formation, there are even stranger theoretical possibilities. Some theories in physics predict the existence of microscopic black holes that could potentially be created in high-energy particle collisions. When the Large Hadron Collider at CERN was being built, some theorists speculated that if extra spatial dimensions exist beyond the three we experience, the effective strength of gravity could be much higher at tiny scales, allowing microscopic black holes to form during particle collisions. If such black holes were created, they would evaporate almost instantly through Hawking radiation, lasting only about 10 to the negative 23 seconds, a billionth of a billionth of a billionth of a second. Despite sensational media coverage, there was never any danger. Even if these micro black holes formed, they'd be gone before they could interact with anything. And despite searching, no evidence for their creation has been found. While we search for exotic black holes, we've also discovered that black holes can pair up in unexpected ways. Binary black hole systems, two black holes orbiting each other, are more common than once thought. Before LIGO's discoveries, we had only indirect evidence for such systems. Now we know they exist throughout the universe, and when they finally merge after spiraling together for millions or billions of years, they create the gravitational wave signals we detect. But there are even more complex configurations. Astronomers have found evidence for triple systems, where three black holes, or a combination of black holes and stars, orbit each other in intricate gravitational dances. Some supermassive black holes may also exist in binary pairs at galactic centers, the result of galaxy mergers that brought two central black holes together. These binary systems have helped resolve one of the great mysteries of black hole astrophysics. The final parsec problem puzzled astronomers for years. When two galaxies merge, their central supermassive black holes sink toward the center of the new combined galaxy. Using stars and gas as gravitational anchors, they can approach to within about 1 parsec, about 3 light years of each other. But theoretical calculations suggested they should stall at this distance, taking longer than the age of the universe to actually merge. This was problematic because we see evidence of merged galaxies with single central black holes, not pairs. Recent simulations and observations suggest the solution involves multiple mechanisms: interactions with stars, gas in the system, and even the presence of a third black hole can help drive the final merger. Gravitational wave observations of supermassive black hole mergers, when we detect them, will help confirm these theoretical solutions. The behavior of matter near black holes creates some of the most spectacular displays in the universe. Accretion disks around black holes can vary dramatically in brightness over time. For supermassive black holes, these variations can happen over days, weeks, or years, as clumps of matter spiral inward or as the rate of material falling in changes. For stellar mass black holes in binary systems, the brightness can change much more rapidly, sometimes flickering on timescales of milliseconds. These rapid variations are caused by turbulence in the accretion disk and by the orbital motion of hotspots in the inner disk. By studying these flickering patterns, astronomers can map the structure of the accretion disk and measure the black hole's spin rate, learning about the orientation and rotation speed of black holes from thousands or millions of light years away. And the innermost regions of these disks are among the most extreme environments imaginable. In the inner accretion disk, temperatures can reach tens of millions of degrees, hotter than the cores of stars. At these temperatures, the disk emits primarily in X-rays. The material is so hot that electrons are stripped from atoms, creating a plasma of charged particles. This plasma interacts with powerful magnetic fields threading through the disk, creating complex dynamics and helping to launch jets. The pressure from intense radiation can actually push outward against the infalling material, creating a luminosity limit called the Eddington limit, the maximum brightness an object can sustain, where radiation pressure balances gravitational attraction. Some black holes appear to exceed this limit temporarily, suggesting complex interactions between radiation, matter, and magnetic fields that we're still working to understand. Beyond the accretion disk lies a region that few discuss, but which is fundamental to the black hole's appearance. The photon sphere is a region outside the event horizon where gravity is so strong that light can orbit the black hole. For a non-rotating black hole, the photon sphere sits at 1.5 times the Schwarzschild radius. This is an unstable orbit. The slightest perturbation will send photons either spiraling into the black hole or escaping to infinity. The photon sphere is what makes the black hole's shadow in images like those from the Event Horizon Telescope appear larger than the event horizon itself. Light from the accretion disk behind the black hole gets bent around it, some completing partial or even multiple orbits before reaching us. This creates the bright ring we see in black hole images, a circle of light trapped in an endless dance around the darkness. We've explored now the full spectrum of black holes, from hypothetical microscopic ones that might have formed at the Big Bang, to the mysterious intermediate mass black holes that remain elusive, from binary systems spiraling toward collision to the glowing accretion disks where matter experiences its final moments. We've seen how light itself can orbit these objects, creating halos of photons in the darkness. But our journey isn't over. What happens inside the event horizon remains one of physics' greatest mysteries. How do black holes connect to the fundamental structure of space-time? And what role will they play in the ultimate fate of the universe? There are still deeper mysteries waiting in the darkness ahead. What lies beyond the event horizon? It's a question that haunts physicists and captures the imagination. We can calculate, theorize, and propose exotic possibilities, but the event horizon represents a fundamental barrier to observation, a cosmic censorship that hides the most extreme physics from our view. The cosmic censorship hypothesis, proposed by Roger Penrose in 1969, suggests that singularities, those points of infinite density at black holes' cores, are always hidden behind event horizons. In other words, nature prevents naked singularities from existing in the universe. This is fortunate, because naked singularities would be regions where the laws of physics break down and are visible to the outside universe, potentially allowing causality violations and other paradoxes. While most physicists believe cosmic censorship holds true, it remains unproven mathematically. Some exotic solutions to Einstein's equations do allow naked singularities under very specific conditions, but whether these could exist in the real universe remains an open question. The singularity itself represents the ultimate unknown. At the singularity, our current theories of physics completely break down. General relativity predicts infinite density and infinite space-time curvature, mathematical infinities that signal the theory has reached its limits. Most physicists believe that a complete theory of quantum gravity, which would unite general relativity with quantum mechanics, is needed to truly describe what happens at the singularity. Some theories suggest the singularity might not be truly infinite, but rather a region of extremely high but finite density described by quantum effects. Others propose that the singularity might be replaced by something else entirely, perhaps a bounce leading to another region of space-time, or a quantum foam of space-time fluctuations. Until we have a working theory of quantum gravity, the singularity remains one of physics' deepest mysteries. But even without understanding the singularity, we can ask what black holes might mean for the universe's future. In the unimaginably distant future, if the universe continues expanding forever, black holes may become the last remaining structures in existence. Stars will have burned out, galaxies dispersed, and even atoms may have decayed. But black holes will persist, at least for a while. Through Hawking radiation, even they will eventually evaporate, but the timescales are staggering. A black hole with the mass of the Sun would take about 10 to the 67th years to evaporate. That's 10 followed by 67 zeros, incomprehensibly longer than the current age of the universe. A supermassive black hole with 1 billion solar masses would take 10 to the 100 years. These are numbers that strain the imagination, eras when the universe will be incomprehensibly older and emptier than it is today. The final evaporation of a black hole might be spectacular. As a black hole evaporates through Hawking radiation, it shrinks, and the smaller it gets, the faster it evaporates. This creates a runaway effect. The black hole becomes hotter as it loses mass, radiating more intensely, which causes it to shrink faster still. In the final moments, what remains of the black hole would explode in a burst of high-energy particles and radiation. For a primordial black hole with the mass of a mountain, this explosion would release the energy equivalent to millions of nuclear bombs. We've searched the sky for these explosive signatures, but haven't found any convincing candidates yet. If primordial black holes exist, and some are evaporating now, detecting their final bursts would be a monumental discovery. While black holes might dominate the far future, they also played a crucial role in the distant past. Supermassive black holes in the early universe present a puzzle. Astronomers have discovered quasars powered by actively feeding supermassive black holes that existed when the universe was less than 1 billion years old. Some of these black holes already contain billions of solar masses. This is surprising because there seemingly wasn't enough time for them to grow so large. If a black hole starts with, say, 100 solar masses from a collapsed star and grows by consuming matter at the theoretical maximum rate, the Eddington rate, it still shouldn't be able to reach billions of solar masses that quickly. This suggests either that the first black holes were unusually massive seeds, perhaps hundreds of thousands of solar masses from the start, or that they grew faster than theoretical limits by consuming matter in episodic bursts or through repeated mergers. These early supermassive black holes had a profound influence on cosmic evolution. The energy released by actively feeding black holes in the early universe helped to ionize the intergalactic medium, the gas between galaxies. After the Big Bang, the universe went through a period called the Dark Ages, when neutral hydrogen filled space, absorbing most light. Radiation from the first stars and from quasars powered by supermassive black holes energized this hydrogen, ionizing it and making the universe transparent again. This epoch of reionization, occurring roughly 150 million to 1 billion years after the Big Bang, fundamentally changed the nature of the universe and allowed light to travel freely across cosmic distances. Black holes, ironically, helped illuminate the cosmos, and black holes continue to influence galaxy formation in the present day. The phenomenon known as AGN feedback, where active galactic nuclei powered by supermassive black holes inject energy into their surroundings, is crucial to understanding why galaxies look the way they do. Without this feedback, computer simulations produce galaxies that are far too massive and contain too many stars compared to what we observe. The energy from black hole accretion heats gas, drives powerful winds, and can even blow gas completely out of galaxies, limiting star formation. This creates a self-regulating system. As a galaxy grows and funnels gas toward its central black hole, the black hole becomes more active, releases more energy, and pushes gas away, slowing both its own growth and the galaxy's star formation. This delicate balance helps explain the relationship between black hole mass and galaxy properties. Black holes also connect to some of the most exotic phenomena in the universe. Tidal disruption events occur when a star wanders too close to a supermassive black hole and gets torn apart by tidal forces. About half of the star's material gets flung away at high speeds, while the other half falls into an elongated orbit around the black hole. As this stellar debris falls inward, it heats up and emits a bright flare of radiation that can outshine the entire galaxy for weeks or months before fading away. Astronomers have now observed dozens of these events, and they provide a unique way to study otherwise dormant black holes. Each tidal disruption event is like turning on a lighthouse to reveal a black hole that was previously hidden in darkness. We've ventured now to the very limits of understanding, to cosmic censorship and unknowable singularities, to the distant future when black holes may be all that remains, and to the distant past when they shaped the evolution of the entire universe. We've seen how they tear stars apart and how they regulate the growth of galaxies. But there's more yet to explore. How do black holes challenge our understanding of space and time themselves? What exotic effects occur in their vicinity? And what might black holes teach us about the fundamental nature of reality? The journey continues into the deepest questions of existence. Black holes don't just warp space. They fundamentally alter our understanding of what space and time even are. Near a black hole, the distinctions we take for granted begin to blur and transform in ways that challenge our everyday intuitions about reality. Inside the event horizon of a black hole, the roles of space and time exchange. In our normal experience, we can choose where to move in space, but we're always pulled forward in time. Time is the dimension we cannot avoid traveling through. But once you cross the event horizon, the inward direction toward the singularity becomes time-like rather than space-like. This means that moving toward the singularity becomes as inevitable as moving forward in time is for us. You cannot avoid it any more than you can avoid your next moment. The singularity isn't just a place you might go. It's a moment in your future that you will reach no matter what you do. This is perhaps the most profound and disturbing aspect of crossing the event horizon. This strange reversal connects to another counterintuitive property. For an outside observer, the surface area of a black hole's event horizon can never decrease. It can only stay the same or increase. When two black holes merge, the resulting black hole's event horizon has a surface area at least as large as the sum of the two original horizons, and usually larger. When matter falls in, the horizon grows. This behavior is remarkably similar to entropy in thermodynamics, a measure of disorder that can only increase in isolated systems. This parallel isn't just coincidental. It led to the discovery that black holes actually possess entropy proportional to their surface area. A black hole is, in a sense, the most entropic object possible, the ultimate state of disorder that matter can achieve. This connection between black holes and thermodynamics reveals something profound about information and reality. The holographic principle, inspired by black hole thermodynamics, suggests that all the information contained within a volume of space can be described by information encoded on the boundary of that region. This idea emerged from realizing that a black hole's entropy, which represents the information content, is proportional to the surface area of its event horizon, not its volume. This is strange. For most objects, information content should scale with volume, but for black holes, it scales with surface area, as if the three-dimensional interior is somehow encoded on a two-dimensional surface. Some physicists believe this principle might apply to the entire universe, suggesting that our three-dimensional reality might be a projection of information encoded on a distant two-dimensional boundary. It's one of the most mind-bending ideas in modern theoretical physics. Black holes also exhibit properties that seem almost biological. Black holes follow what physicist John Wheeler called the no-hair theorem, a somewhat whimsical name for a profound concept. The theorem states that black holes can be completely described by just three properties: mass, electric charge, and angular momentum, spin. All other information about what fell in the hair is lost. It doesn't matter if you feed a black hole stars, planets, or antimatter. If the mass, charge, and spin are the same, the resulting black holes will be identical. This extreme simplicity is both elegant and troubling. It suggests that black holes are the ultimate erasers of information, destroying all the complexity and detail of whatever falls in. Though, as we discussed earlier, this apparent information loss remains one of physics' deepest puzzles. The spin of a black hole, one of those three fundamental properties, has measurable consequences. Astronomers can measure how fast a black hole is spinning by observing the ion emission lines from its accretion disk. Ion atoms in the hot inner disk emit X-rays at specific frequencies, but the extreme environment near the black hole distorts these emissions in characteristic ways. The rotation of the black hole drags space around with it, causing light from the approaching side of the disk to be blue shifted and from the receding side to be red shifted. The shape of the resulting distorted emission line reveals the black hole's spin. Using this technique, astronomers have found that some supermassive black holes spin at more than 90% of the theoretical maximum. They're rotating at a significant fraction of the speed of light at their event horizons. These rapidly spinning black holes can extract energy in a remarkable way. The Penrose process, proposed by Roger Penrose in 1969, describes a method for extracting energy from a rotating black hole. In the ergosphere, the region just outside the event horizon, where space-time is dragged along with the black hole's rotation, it's theoretically possible for a particle to split into two, with one particle falling into the black hole with negative energy from the black hole's perspective, while the other escapes with more energy than the original particle had. This process would slow the black hole's rotation slightly while releasing energy. A more efficient version, involving magnetic fields, called the Blandford-Znajek process, is thought to power the relativistic jets from some active galactic nuclei. In principle, an advanced civilization could use these processes to extract up to 29% of a black hole's mass energy far more efficient than nuclear fusion. Black holes also create natural laboratories for testing extreme physics. Near the event horizon of a black hole, quantum effects become important even for macroscopic physics. The extreme curvature of spacetime can create particle-antiparticle pairs from the vacuum, virtual particles that quantum mechanics allows to briefly appear and then annihilate. Near the event horizon, one particle might fall in while the other escapes, which is the mechanism behind Hawking radiation. But there are other exotic predictions. Some theories suggest that the vacuum near a black hole might be unstable in unusual ways, or that the event horizon itself might have quantum structure, perhaps looking fuzzy or fluctuating at the smallest scales rather than being a perfectly smooth boundary. Testing these ideas requires observations that push the limits of our technology. The environment around black holes teaches us about physics in other ways too. Black holes serve as cosmic particle accelerators and gravitational wave laboratories that we could never build artificially. The Large Hadron Collider, humanity's most powerful particle accelerator, reaches energies of about 14 trillion electron volts. Near black holes, particles routinely reach energies millions of times higher. When black holes merge, they test general relativity in the most extreme conditions: strong gravity, high speeds, and dynamic spacetime all combined. Each gravitational wave detection provides a new test of Einstein's theory, and so far, it passes every test. But physicists remain alert for any deviation that might hint at physics beyond general relativity, perhaps a quantum correction to gravity or evidence of extra dimensions. We've traveled deep into the theoretical heart of black holes, where space and time exchange roles, where entropy reaches its maximum, where the three-dimensional universe might be encoded on a two-dimensional surface. We've seen how black holes can be described by just three numbers, how their spin can be measured and even harvested for energy, and how they serve as natural laboratories for the most extreme physics imaginable. Yet mysteries remain. What would you actually experience falling into a black hole? How do black holes connect to the deepest questions about the nature of reality? And what surprises might future observations reveal? Let us descend further toward the heart of the mystery. Imagine for a moment that you could approach a black hole, not just calculate what would happen, but truly experience it. The journey would be unlike anything else in the universe, a voyage where the very fabric of your reality transforms with every meter traveled. As you approach a black hole, one of the first things you'd notice is gravitational lensing, the bending of light around the massive object. Stars behind the black hole would appear to shift position, creating multiple distorted images. The black hole itself would appear as a dark sphere against the background of space, but with a strange halo of bent light surrounding it. As you drew closer, this effect would become more dramatic. Stars directly behind the black hole would be smeared into a bright ring, an Einstein ring. The entire visible universe would begin to compress into a shrinking circle behind you, while the darkness ahead would expand. You'd be able to see more and more of the universe in your backward view, as light from wider angles gets bent into your field of vision. The visual distortions would become increasingly surreal. If you were falling toward a rapidly spinning black hole, you would witness bizarre optical effects, due to the dragging of space-time. Light from the accretion disk would appear asymmetric, one side brighter than the other due to relativistic beaming, where material moving toward you at near light speed appears much brighter. You might even see multiple images of the same region of the disk as light takes different paths around the black hole before reaching your eyes. Some photons might orbit the black hole several times, creating ghost images of objects at different positions. The view would be a kaleidoscope of distorted, multiplied, and time-delayed images, a hall of mirrors created by curved space-time itself. But the visual strangeness would pale compared to the temporal effects. As you fall inward, you would see the universe outside accelerate. Light from distant stars, redshifted by your motion into the black hole's gravity well, would show you the future. If you could somehow survive the tidal forces and had a powerful enough telescope to watch Earth, you'd see time pass faster and faster there. Days would turn to years, years to centuries. For a large enough black hole, you might witness the entire future history of the universe, compressed into your final moments. Stars burning out, galaxies evolving, the cosmos transforming, all in the blink of an eye, all while the darkness ahead grew larger and more absolute. Once across the event horizon, your fate would be sealed, but your experience wouldn't immediately end. For a supermassive black hole, the transition across the event horizon would be smooth and unremarkable. The gravitational gradient, the difference in gravitational pull between your head and feet, would still be relatively gentle at that point. You might not even realize you'd crossed it. There would be no physical barrier, no sensation of impact, nothing to mark the moment when escape became impossible. You could still see the outside universe for a short while, now compressed into an ever-shrinking bright spot behind you. But ahead, in the direction of the singularity, there would be only darkness, a darkness that, by the geometry of space-time itself, is now your inevitable future. The interior structure of a black hole remains largely theoretical, but some possibilities are truly exotic. Some solutions to Einstein's equations suggest that rotating black holes might contain a Cauchy horizon, an inner boundary where the predictability of physics breaks down. Beyond the event horizon, but before the singularity, there might exist a region where information from the infinite future of the outside universe pours in, creating an unstable boundary where time travel paradoxes and causality violations become possible. Most physicists believe this inner horizon would be unstable, that quantum effects or classical instabilities would destroy it, replacing it with something else, perhaps a more conventional singularity. But the true nature of a black hole's interior remains one of physics' greatest unknowns, accessible only through mathematics and imagination. Black holes might even connect to parallel universes in some theoretical frameworks. Certain mathematical extensions of Einstein's equations describe what are called maximally extended black holes, theoretical constructs that include not just a black hole, but also a white hole and connections to parallel universes. A white hole would be the time reverse of a black hole, a region of space-time where matter and light can only exit, never enter. These solutions suggest the possibility of traversable pathways through black holes to other regions of space-time or even other universes. However, These solutions are almost certainly not physically realistic. They require perfect symmetry and eternal existence, with no formation process. Real black holes that form from collapsing stars don't have these properties. They're mathematical curiosities that reveal the richness of general relativity, but probably don't describe actual cosmic objects. Yet some speculative ideas about black holes are taken more seriously. The fuzzball proposal, developed in string theory, suggests that black holes might not have singularities or sharp event horizons at all. Instead, at the quantum level, a black hole might be a fuzzball, a tangled ball of fundamental strings and other quantum objects, without any interior empty space. From far away, this would still look and behave like a classical black hole with an event horizon. But up close, at quantum scales, the event horizon would be replaced by a highly excited quantum state. If true, this would resolve the information paradox, because information wouldn't truly fall into an inaccessible interior. It would be encoded in the structure of the fuzzball itself. This remains speculative, but it's an active area of research in theoretical physics. Black holes also appear in popular culture and have captured human imagination in profound ways. The portrayal of black holes in science fiction has evolved dramatically as our scientific understanding has improved. Early depictions often show them as cosmic vacuum cleaners or literal holes in space. But the 2014 film Interstellar raised the bar significantly, working with physicist Kip Thorne to create scientifically accurate visualizations of a supermassive black hole called Gargantua. The visual effects team used equations from general relativity to render the gravitational lensing, accretion disk, and light distortions. The resulting imagery was so detailed that it led to scientific papers about visualizing black holes. While some liberties were taken for dramatic effect, Interstellar showed millions of people what it might actually look like to approach and orbit a black hole, bridging science and art in unprecedented ways. And our understanding continues to evolve through observation. X-ray telescopes have revolutionized our ability to study black holes. Because the hot material in accretion disks emits primarily X-rays, space-based X-ray observatories like NASA's Chandra X-ray Observatory, ESA's XMM Newton, and others have been crucial for detecting and studying black holes. These telescopes have found thousands of black hole candidates, mapped the high energy emission from jets, observed the X-ray echoes of material falling into black holes, and detected the ion emission lines used to measure black hole spin. Each new X-ray observation adds to our understanding, revealing the behavior of matter in the most extreme gravitational environments in the universe. We've journeyed now through the experience of falling toward a black hole, witnessing the distortion of space, the acceleration of time, and the strange visual phenomena that would mark your final moments. We've explored theoretical possibilities from Cauchy horizons to fuzzballs, from white holes to the intersection of black holes and popular culture. And we've seen how our observational tools continue to reveal new aspects of these cosmic enigmas. As we near the end of our journey, questions linger. What have we learned about the universe from studying black holes? What mysteries remain unsolved? And what might future generations discover about these ultimate cosmic mysteries? The final stretch of our journey awaits.